You open a government website to pay your tax. You click submit, and it tells you the service is unavailable. One person, one form, nothing. Meanwhile, in November 2022, Taylor Swift's Eras Tour presale hit Ticketmaster with 3.5 billion total system requests, 4 times its previous peak. More than 2 million tickets sold in one day. About 15% of interactions still had problems, so nobody's calling that magic, but it is a very good pressure test. So let's run our own. 1 million requests hit our ticket site in 1 second, and almost none of them are going to reach the database. About 11,000 will. The other 989,000 stop somewhere along the way, and every place they stop is a different idea. We're going to build all of them, starting with one server, because right now, that's all we own. Here's our one server. First, we load test it, which just means we send it more and more traffic and watch where it breaks. It answers in under 1/4 of a second, all the way up to 500 requests per second. Push past that, and it doesn't get faster, it gets slower, because requests start piling up inside it. So 500 is our tested number. It belongs to this server on this day. It's not a law of the internet. Now send it 1 million. The first 500 start moving. The rest wait until they time out. The server doesn't care that the crowd is famous. So we add more servers, and we put a load balancer in front of them. Its whole job is to take each request and hand it to one healthy server, so all of them work at the same time. It also keeps checking whether they're alive, and a server that stops answering gets pulled out before any new traffic reaches it. We run 2 load balancers, because swapping one single point of failure for a better looking one isn't a fix. So 1 million requests, 500 each. That's 2,000 servers. 2,000 servers to sell tickets to a concert. Before we buy 2,000 servers, one question. Do all 1 million requests actually need one? Nah, not even close. Look at what people are asking for. 800,000 of them just want the public event page, the tour photo, the seat map, the style sheet, the scripts. Same files, same bytes for everyone. So before tickets go live, we copy those files onto servers spread around the world. Together, those servers are a Content Delivery Network, or CDN. Cloudflare is one you've almost certainly used without noticing. When a fan opens the page, the nearest copy answers, and the request stops right there. Our application never sees it. The fans are refreshing like it's a competitive sport. The CDN is completely unbothered. So 800,000 stop at the edge, and 200,000 keep going inward, which changes the shopping list. 200,000 at 500 per server is 400 servers. We sized a fleet of 2,000. We need 400. We'll actually run 500, not 400. Running every machine at exactly its limit leaves nothing for a bad minute, so those extra 100 servers are our headroom. And the edge doesn't get to answer everything. Anything personal and anything that takes money is different for every single person, so the CDN isn't allowed to invent those. 200,000 requests now arrive at a fleet of 500 servers, and that creates a brand new problem. You log in. That request lands on server 1. Your next request lands on server 3, which has never met you, so it asks you to log in again. Very scalable. So when you log in, we hand your browser a cookie, a small piece of text your browser sends back every time it talks to us. Inside it is nothing but a random ID. The actual session, who you are and what you're allowed to do, lives in one shared store that every server can read, like Redis. Now it doesn't matter which server you land on, because they all look up the same session. That cookie is worth stealing, so we lock it down. It only travels over HTTPS, so nobody can read it off the network. JavaScript can't touch it, and it never gets sent to another website. Your neighbor doesn't get a free VIP pass just because your next click landed on a different machine. You may have heard of JWTs here. A JWT is a signed token, so any server can check it without looking anything up, which is genuinely faster. We're not using one because a signed token stays valid until it expires, and we need to be able to cancel someone's ticket hold right now. Everything now lands on one database, and we're treating two completely different jobs as if they're the same. Opening an event page and checking whether seats are left is a read. It looks at the truth. Reserving seat A17 is a write. It changes the truth. Those two deserve different treatment. For reads, we can make copies of the database, called read replicas. The main database, the primary, sends every change out to them, and they answer read queries, which spreads read traffic across several machines instead of one. The catch is that the copy arrives slightly late, so a replica can be a fraction of a second behind. For the same question asked over and over, we use Redis instead. 190,000 people are checking availability for the same few sections, so we keep that answer in memory for 1 second. 95% of those checks find it already sitting there. That turns 190,000 questions into about 9,500 that actually reach storage. The database gets asked once and then gets to sit down. Both of these can be slightly out of date, and that's the line you have to respect. A 1 second old answer is fine for telling someone seats are selling fast. It is not proof that seat A17 is still free. The cache can help you browse. It can't sell you the seat. Two people are looking at seat A17. Both screens say available. Both press buy in the same tenth of a second. Read, then write. Read, then write. And now two people own one chair. The fix is to stop asking and then telling, and do both in one move. The database runs a single instruction. Change A17 from available to reserved, but only if it is still available. One buyer changes one row and gets the seat. The other changes 0 rows and gets sold out. There's no gap in the middle for anyone to slip into. That settles who owns the seat. It does not make one database faster. So to handle more writes, we split the data across several databases. Each one is called a shard, and something has to decide which shard a row belongs to. If we pick the concert as that key, every single Eras Tour purchase has the same key and lands on the same shard. 3 databases, 3 bills, one of them doing all the work. Excellent. So we key on the concert and the seat together. Seat A17 always goes to the same place. Seat A18 might live somewhere else, and the writes spread out. And notice those are 2 separate jobs. Sharding decides which machine. The conditional update decides which buyer. Neither one does the other's work. Here's something that happens at 3 in the morning. One of our cache machines dies. We had 10, now we have 9. So how do we decide which machine holds which key? The simplest way is to take the key, turn it into a number, and divide by how many machines we have. The remainder picks the machine, which works beautifully right up until that number changes. Divide by 9 instead of 10, and almost every key gets a different answer. Nearly everything we cached is now in the wrong place. None of it is wrong, it's just filed under the old rules. Consistent hashing fixes the filing. Put every machine on a circle, put every key on the same circle, and each key belongs to the next machine going clockwise. Now when a machine leaves, only the keys sitting just behind it have to move. Everything else stays exactly where it was. But read what that actually says. Consistent hashing decides where a key belongs. It does not put the data there. So every shard still keeps replicas of itself, and when a primary dies, one of its replicas is promoted and the map is updated. Skip that part, and consistent hashing will confidently route you to a brand new empty machine. The routing is correct. The data is gone. 10,000 buyers press buy in the same second for 5,000 remaining seats, and our write path can safely commit about 2,500 per second. So where do the other 7,500 go? Nowhere. They sit inside the application and its database connections, waiting, while latency climbs, clients time out, and every timeout gets retried. Congratulations! We built a queue and hid it in the most expensive place we own. And yes, autoscaling. It spots the spike, starts new instances, opens connections, warms them all up, and they are ready comfortably after a 1-second burst has finished. Lovely. Autoscaling is for traffic that stays high. A sale with a start time needs its capacity already standing there when the clock hits 0. So we move the queue to the front, where waiting is cheap and people can see it. A waiting room at the edge lets in 2,000 buyers a second, deliberately under the limit, and 8,000 keep their place in line without touching the application at all. The burst hasn't gone anywhere. It just can't all come inside at once. Everyone we let in goes into a durable queue, which just means the purchase is written down somewhere safe and stays there until a worker confirms it's finished. Workers pull from that queue only as fast as the database can safely commit, so the waiting now happens in the queue instead of inside somebody's browser. But the queue has a ceiling. If purchases keep arriving faster than workers can finish them, it fills up, and a full queue is just our hidden backlog again, in a cheaper room. So the queue tells the waiting room how full it is. As it fills, the waiting room admits fewer people. When it reaches the ceiling, the door shuts completely, and nobody new comes in until the workers catch up. Pressure at the back of the system reaches all the way to the front, and changes what the front is willing to accept. That is back pressure, and it's the difference between a system that gets slower and a system that falls over. One more thing can go wrong, and it's a good one. A worker picks up a purchase, reserves seat A17, and then crashes. Not before doing the work, after. It just never got to say so. The queue has no idea any of that happened. All it knows is that nobody confirmed, so it does the sensible thing and delivers the same purchase again, which is how one person gets charged twice for a seat the system then tells them they didn't get. So every purchase carries an idempotency key, one ID for one attempt, created the moment the buyer presses buy, and carried through every retry. The first time a worker sees that key, it does the work and saves the result under that key in the same transaction, so the seat and the receipt are written together, or not at all. The second time, the key is already there. The worker doesn't reserve anything and doesn't charge anything. It returns the answer it gave the first time. 2 deliveries, 1 ticket, 1 charge. And this is a different job from the conditional update in the seat chapter. The conditional update stops 2 different buyers from taking 1 seat. The idempotency key stops 1 buyer's purchase from happening twice. Neither one covers for the other. Right, let's follow that million and watch where everyone stops. 800,000 want the public page. They stop at the CDN and never come near us. That leaves 200,000. 190,000 are checking availability, and 95% of them get their answer straight out of Redis and stop there. That's 180,500 gone. 9,500 reach storage, spread across replicas. 10,000 want to actually buy. 2,000 are let in through the waiting room, and 8,000 keep their place in line. Every purchase that gets in is held in the durable queue, carries an idempotency key so a repeat delivery can't charge anyone twice, lands on the shard that owns that seat, and finishes with 1 conditional update that gives the seat to exactly 1 person. So add up everything that reached the database this second. 9,500 reads, 2,000 writes, about 11,000 out of a million. Meanwhile, our tax website is still down. 1 person, 1 form. Turns out you can fail at any scale. And that's really the point. A site doesn't survive a million requests a second by owning 1 enormous server. It survives because almost nothing gets that far. The same page answered at the edge, the same question answered out of memory, the same purchase never done twice, and 1 seat given to exactly 1 person on purpose. It isn't one hero, it's a series of good places to stop.